This is Long ISP desktop mini fridge. This project has many key components that make it function the way it does, and I'm very happy with the end result. Let's start with the user interface. So on the side here, we have a 1.8 inch measured diagonally Adafruit full color TFT LCD display, 3 PBNO buttons, and 1 rugged metal button from Adafruit. On the inside, we have a 1 limit switch, 2 12-volt 3-amp LEDs, and 1 LM35 temperature sensor. Then we have a 1 12-volt DC CPU fan to disperse the cold air inside of the fridge liner. The fridge door is attached with hinges and a latch system over. The backbone of this project is sandwiched in between 2 heat sinks over here and inside this white foam. It is called a Peltier tile. Thermoelectric coolers, or Peltier tiles, operate according to the Peltier effect. The effect creates a temperature difference by transferring heat between 2 electrical junctions. A voltage is applied across joined conductors to create an electronic current. When the current flows through these junctions of the 2 conductors, heat is removed at one junction and cooling occurs. Heat is deposited at the other junction. Thermoelectric coolers act as a solid-state heat pump. Each has an array of alternating N and P-type semiconductors. The elements are soldered between 2 ceramic plates, electrically in series and thermally in parallel. The fridge is divided up into 4 main 3D printed parts. The bottom over here, the liner right here, then the middle section here where the food is housed, and then the door over here. Everything comes apart very simply, all coming together at this middle part over here. First, the top half is friction fit to the bottom half, then there's a liner, and then the bottom half is here where all the electronics are stored. Lots of the design changes included small details such as the vent holes at the bottom and the placement of buttons. A top-down view of the electronics shows a relay module, a permabroto board hidden underneath there that has a 328P, a 555 timer latch circuit for this rugged metal button, the connections for the display over here, and the 3 buttons over here. Then there's also DC power coming through the bottom with 12 volts, 3 amps. This is version 1 PCB, featuring an L298 motor driver, a 555 latch circuit, and an Atmel 328P. The circuit board is divided into 2 different circuits as mentioned before. The first is the latch circuit, which is on this side of the board, and then the H-bridge circuit, which features the back half of the board and this side of the board over here. So this is the L298 motor driver. This is the L298N motor driver full bridge IC. As you can see here, this is a non-soldered version and it has lots of pins. On here, on the custom PCB, is the version with a passive heatsink with an option for an active cooling with fan. So the first iteration of my control electronics to use the L298N full bridge driver to create an H-bridge for cooling and heating. The main features of the L298N include a high working voltage up to 46 volts, large output current, and a full bridge driver with 2 H-bridges. ENA and ENB pins are speed control pins for device A and B, while IN1 to IN2 and IN3 to IN4 are direction control pins for device A and B. It also uses TTL logic levels, and external diodes are a requirement when using this IC. When turning a load on or off, a spike in current occurs. These diodes protect the microcontroller from the current spikes. Fast-changing diodes, such as Schottky diodes, which you can see over here, are recommended when testing the L298N